Welcome to the deep dive. This is where we synthesize all that complex research and news flying around, distilling it into the key nuggets you really need to know fast. We want to give you that shortcut to understanding.
Exactly, giving you the facts, the context, without drowning you in information.
And today, yeah, we're looking at something big, a major development, really, in the open source AI world.
That's right. We are diving deep into the release of two really quite powerful open-weight reasoning models. They're called GPT-OSS 120B and GPT-OSS 20B, and they come from a well-respected AI lab.
Yeah, and this isn't just, another model drop. It feels like potentially a real shift. I mean, historically, that top-tier reasoning power, that was locked behind APIs, right? The proprietary models, the O-series we often talk about. So our mission for you today is to get straight to the implications. How do these models hit near-frontier performance but stay hardware efficient? And what does their safety testing signal for open-weight AI going forward?
And the core idea, the thesis here, is pretty straightforward. Performance that you used to only get from systems like OpenAI's, say, O4 Mini.
Right.
It's now potentially available to almost any developer, any organization, running on pretty standard enterprise gear, and, crucially, under a very flexible commercial license. It's about democratizing that cutting-edge capability.
Okay, let's unpack that. Starting maybe with the business side of things, licensing can seem dry, I know, but for open models, it's everything. Why is the license here such a big deal?
It really is. It boils down to freedom, essentially. These models use the Apache 2.0 license.
Apache 2.0, okay.
Yeah, highly permissive. So if you're building a business on this, you can use the model freely, customize it, change it, and this is key, deploy it commercially. No copyleft strings attached.
Meaning you don't have to share your own changes back if you build on it.
Exactly. You can fork it, build your own secret sauce on top, and you don't owe royalties. You don't worry about weird revenue caps some other licenses might have. It's true commercial freedom.
That kind of freedom is huge, but usually that freedom with big models meant, well, needing a server farm in your basement.
Yeah, pretty much.
I remember just a few years back, running a 7 billion parameter model locally felt like a major project. Now we're talking 120 billion parameters. How did they manage to pair this permissive license with, actual accessibility, low-cost hardware efficiency?
That's really where the innovation shines, I think. They were laser-focused on delivering strong performance, real-world stuff, but at low cost. Just look at the numbers. The big one, GPT-OSS 120B.
Yeah.
It has 117 billion parameters total, but it runs efficiently on a single 80 gigabyte GPU.
A single 80 gig GPU.
Yep, and the checkpoint file itself, the model data, is about 60.8 gigabytes, manageable.
Okay, a single 80 gigabit card. That definitely moves it out of the research collab only category and into deployable tool territory for many companies.
Absolutely.
But then there's the smaller one, GPT-OSS 20B. That sounds like it's aimed somewhere else entirely, maybe edge computing.
Precisely. The GPT-OSS 20B model, it's got 21 billion total parameters, checkpoint size around 12.8 gigs.
Yeah.
It's really optimized to run on devices with just 16 gigabytes of memory.
16 gigs, like potentially on a high-end laptop or embedded system.
Exactly. Think local inference, super fast responses, and crucially, those use cases where data privacy is absolutely paramount. The data never needs to leave the device.
So massive power, surprisingly low memory footprint. What's the magic? What's the architectural trick that makes this possible?
A combination, really. Architecture and compression. Both models are what we call autoregressive mixture of experts transformers. MOE for short.
Mixture of experts, MOE. Okay, I've heard that term. How does that help with efficiency?
Well, think of it like this. The model has this enormous pool of knowledge, right? 117 billion parameters. But for any one specific task, any single calculation or token prediction, it only brings in a small fraction of those parameters, a specialized subset of experts.
Ah, okay, so it's like having a giant library, but you only pull down the few relevant books you need for a specific question instead of reading the whole library every time.
That's a great analogy. You get the benefit of that vast knowledge base, but the computational cost for each step is much lower. For the 120B model, it only activates about 5.1 billion parameters per token it processes.
Only 5.1 billion out of 117 billion.
Yeah. And the 20B model, it activates just 3.6 billion per token. It's this sparsity using only a fraction of the total, combined with something called native MXFP4 quantization that really slashes the memory requirement.
Okay, MXFP4 quantization, that sounds technical. Break that down for us.
Sure. Think of it as a really, really efficient way to shrink the data size of the model's weights, those billions of numbers that define the model.
Hmm.
Instead of storing them with lots of decimal places, high precision,
Right.
MXFP4 basically squishes them down into tiny 4-bit representations.
Yeah.
It drastically cuts the amount of GPU memory needed to hold the model
Without wrecking the performance.
without significantly sacrificing accuracy. Yeah. It's a clever trade-off. And it's what makes running that 120B model on a single 80GB GPU actually feasible.
Okay. Efficiency sorted. Now, the really juicy part, performance. How do these open weight contenders actually stack up against the big closed models, the proprietary ones? The benchmarks seem, well, pretty surprising.
They really are. On core reasoning tests, the standard benchmarks people use, GPT-OSS 120B, is getting results very close to OpenAI's O4 Mini.
Near parity with 4 Mini.
Yeah. And the smaller 20B model is performing roughly on par with OpenAI's O3 Mini. So, the best open weight models are now seriously competing with some of the established proprietary players.
But it wasn't just general reasoning, right? There was one area where the results seemed particularly strong, almost unexpectedly so. Tell us about the health bench evaluation.
Ah, yes. Health bench. This is where it gets really interesting. The 120B model, especially when you tell it to use high reasoning effort, we'll get to that, perform competitively with the very best closed models.
Competitive.
Actually, in some cases, outperforming them. On the harder parts of Health Bench, the hard evaluation, it beat models like GPT-4o, O1, O3 Mini, and even a 4 Mini.
It outperformed GPT-4o and a 4 Mini on a hard health benchmark.
On that specific hard subset, yes. It's a significant result. It suggests a major shift in the performance you can get for the cost, especially in areas like health intelligence, where privacy and running things locally can be critical.
That is huge for health tech, for research. Wow.
It is. But, and this is really important, we absolutely have to include the disclaimer from the source material here.
Okay, yes. Safety first.
While the performance is impressive, these models are not replacements for doctors or medical professionals. They aren't intended for actual diagnosis or treatment. They're tools, incredibly powerful tools, but not substitutes for human medical expertise.
Got it. Very important distinction. Okay, so beyond raw knowledge and reasoning, how do they function as agents? Can they use tools? Follow complex instructions?
Yes, they show strong capabilities there too. Good tool use, effective Q-shot function calling, meaning they can learn to use new tools, from just a couple of examples, and they handle complex chain of thought, or QT, reasoning quite well.
We see that reflected in specific tests.
Yeah, benchmarks like TalBench and Codeforces, which really push models on multi-step coding and math problems, show good results. Plus, they handle long inputs up to 128,000 tokens of context length.
128K context, that's substantial. And you mentioned something earlier, variable effort reasoning. That sounds like a practical feature developers would appreciate.
Oh, absolutely. This is really neat. Developers can basically tell the model how hard to think using a simple instruction, a system message. Low, medium, or high effort.
Why is that useful?
It lets you balance performance versus cost and speed. Need a quick, cheap answer for a chatbot? Use low effort. Needed to really crunch on a complex legal document analysis or, say, solve a tough math problem? Crank it up to high effort.
And high effort isn't just a label, right? You mentioned it really uses more resources.
Definitely. On some of those hard competition math problems, like from the AM contest, the 20B model, when set to high effort, generated chain of thought reasoning that was, get this, over 20,000 tokens long to arrive at the solution.
20,000 tokens of thinking out loud, basically.
Exactly. It shows the model can do that deep deliberation when needed, but the developer controls the dial, controls the cost and latency trade-off. Very practical.
Okay, so incredibly powerful, flexible, efficient, but open weight. That immediately brings up safety concerns. How did the lab tackle the risk of misuse, especially since anyone can download and potentially fine-tune these things?
They took safety very seriously, implementing multiple layers. It started right back in pre-training. They filtered out harmful data sources, specifically mentioning content related to CBRN risks.
CBRN, let's clarify that. Chemical, biological, radiological, nuclear. So the really dangerous stuff was filtered from the get-go.
Correct. Then, after the initial training, they used techniques like deliberative alignment and something called the instruction hierarchy. This is designed to teach the model when to refuse harmful requests and how to resist prompt injection attacks.
The instruction hierarchy, how does that work?
It sets a pecking order for instructions. System instructions rank highest, then developer instructions, then the user's prompt, then the assistant's own generated text, and finally tool outputs. The idea is that a lower-level instruction, like a user trying to trick it, shouldn't override a higher-level safety rule set by the system or developer.
So the developers don't do X rule, should ideally trump a user trying to persuade it to do X.
That's the goal. Now, the research paper is commendably honest here. It notes a nuance.
Uh-oh.
Well, not, oh, but it's important. While the models are very good at resisting known jailbreaks, they perform about as well as a 4 mini on a benchmark called strong reject. They're generally less reliable than a 4 mini at strictly enforcing that hierarchy, when a clever user really tries hard to override developer or system rules.
Okay, so robustness against known attacks is good, but enforcing custom rules against determined users is maybe an area for caution for developers.
Precisely. It's something developers need to be aware of when building applications on top. Don't assume the hierarchy is unbreakable.
What really caught my eye in their safety work was this concept of adversarial fine-tuning. It sounds like they tried to build the worst possible version of their own model.
That's essentially it, yeah. They simulated what a sophisticated attacker might do. They took GPT-OSS 120B and deliberately fine-tuned versions of it to maximize harmful capabilities,
Yeah.
like generating biological risk information or finding cybersecurity vulnerabilities.
That's sort of red teaming on steroids.
Exactly. The goal was to find the absolute ceiling. If someone tries to make this model as dangerous as possible, how dangerous can it get?
And the results. Did this confirm everyone's worst fears about powerful open models?
Actually, the findings were quite reassuring, relatively speaking. Even these maliciously fine-tuned versions, pushed to be as bad as possible, did not reach the high capability thresholds defined in the standard preparedness framework for biological, chemical, or cyber risks.
So even the evil twin version didn't cross the highest danger lines.
Correct. It suggests the base model has some inherent safety constraints, even if pushed.
That has pretty big implications for the whole open source debate, doesn't it? There's constant criticism about releasing powerful models openly.
It does. And the lab's analysis went further. They concluded that releasing these specific models is unlikely to significantly push the frontier of dangerous capabilities already out there in the open ecosystem.
Why not? Because other models are already capable.
Essentially, yes. Their data show that other powerful open-weight models already exist. They mentioned Qwen 3 Thinking and Kimi K2 specifically, that perform similarly to the adversarially fine-tuned GPT-OSS 120B on many of these biosecurity tests.
So the risk profile didn't dramatically change with this release because comparable capabilities, unfortunately, were already accessible.
That seems to be their assessment based on the comparative data.
Okay, one last critical point before we wrap up. You mentioned chain of thought, the model showing its work. There's a warning attached to that, right?
A very important one. The models do provide their full chain of thought reasoning. This is fantastic for researchers who want to understand how the model reached an answer or to build systems that monitor its reasoning process.
A nut.
But this COTI output was not trained with direct supervision to be safe or polite or even necessarily truthful in its intermediate steps. The model wasn't incentivized to hide potentially problematic thoughts, internal hallucinations, or reasoning paths that might seem harmful if taken out of context.
So the internal monologue might contain rough drafts or weird ideas?
Exactly. Therefore, the strong recommendation is never show the raw chain of thought output directly to end users in a deployed application. It's a research tool, a debugging tool, not something for public consumption.
Got it. Rocco is for developers and researchers only. Okay, let's try and bring this all together. What's the big picture takeaway here?
We're seeing near-frontier AI reasoning power, performance, close to things like a 4 mini,
Right.
packaged under a fully permissive, commercially friendly Apache 2.0 license,
Crucial for business.
and delivered using this mixture of experts architecture combined with quantization, making it efficient enough to run on a single, reasonably accessible 80 GB GPU.
It really feels like a lowering of the barrier to entry for high-end AI.
Absolutely. It opens doors for sectors that might have been resource-constrained before. Think specialized research groups, nonprofits, global health initiatives, smaller AI startups. And the fact that it launched with backing from major players, AI, Sweden, Snowflake, Azure, NVIDIA, were mentioned signals that the ecosystem is ready to support its adoption.
So we've got this unprecedented reasoning power now open, customizable, and genuinely hardware efficient.
Which leads us, I think, to a really interesting final thought for you, the listener, to mull over.
Given that surprising strength we saw in HealthBench and the model's inherent suitability for privacy-preserving local deployment, how quickly might we see these kinds of powerful, open-weight, cost-effective models become the dominant tools in highly specialized, high-stakes fields? Fields that, until now, often relied on expensive, proprietary closed systems, perhaps partly due to privacy or control needs. Is this the start of that shift?